It would be amazing, wouldn't it? All right. So, hardware shaders. Why do you think I want you to know anything about hardware shaders? And what is it? What's a hardware shader, anyone?
It's not the software.
What kind of hardware is it? I mean, technically all things run on hardware, right?
I mean, the engine, things that run the engine.
What? It's for running on graphics cards, right? So these are shaders that run to display graphics in your games. Who's interested in gamey stuff? A few people. Okay, so what's the biggest difference between game shaders and the stuff you do for offline rendering?
They have to run really fast.
Yeah, it's all about performance. And not all hardware is created equal, right? Like the 5090 in my office is a lot more powerful than the Quest's GPU or your phone, right? And so you have to be, like when you're doing game stuff, you have to be aware of what your target platform is. But it's also good to understand how the whole system works. So, let me give you just a quick overview. There's multiple languages for hardware shaders. We have GLSL, which is the OpenGL shading language. Then there's HLSL, which is high-level shading language. And then you get all kinds of other things because people like to expose the functionality that they want for their rendering system. So for the shaders that we were writing for Meta, we had our own shading language, which is just like a repackaging of hardware shader language. Well, what's that system called? Spark shading language? You guys are familiar with Spark? Maybe, maybe not. Are you familiar with lenses for Snapchat? Okay, so Snapchat allows you to do stuff like recording pictures of yourself and then sticking a cat face on it, right? Spark is a system written for, I honestly don't know what it was written for. But Meta used it for doing their same type of, same analog to Snapchat. And so the engineers that wrote Spark shading language, they included the functionality they wanted. And even though ultimately it gets compiled down to run on the same types of hardwares, different functionality can be exposed by different shading languages. So for this project, we're going to use Godot. Is anybody familiar with Godot? Everyone familiar with Unity and Unreal? Okay, so these are different game engines, right? Unreal is the super heavyweight one. You know, if you try to run Unreal on your laptop while it's not plugged in, you will just count on the battery draining extremely quickly. And Unity is another game engine. It's not nearly as resource intensive, mostly because Unity has a proper UI and Unreal uses the game engine to render the UI. And so while you are using the editor, you are also playing a high-end game. And then Godot is a very lightweight open source game engine. It's installed on your computers here. You can download it easily enough at home. And it is its own thing. I chose it for this because it's a lot lighter weight than having to deal with Unity or Unreal when it comes to doing just like a simple put together shader and have it render on screen. All those other systems are super capable. They have node network systems and you can do all kinds of fun stuff. We are just going to write shaders by hand. So I'm not expecting miracles out of this. I just want you guys to get a brief understanding of how the system works. So let me talk a little bit about how to start it up, and then we'll talk about a little bit of theory. Okay? So let's see. Oh, there's some online resources. One is called the Book of Shaders. It's at thebookofshaders.com. In the Learning Suite, under Resources or Content, there is an entry that has links to both of these. So the Book of Shaders is it. I think all the examples are in GLSL. There is documentation in Godot that kind of gives you what are the analogs between GLSL and Godot shading language. I'm not having you write it in GLSL just because using the Godot stuff simplifies a lot of boilerplate stuff. Then there's the Godot documentation, which is pretty good. It has lots of examples. It has a whole section on shading languages, and it will tell you like data types, flow control, how to basically all the stuff you need to know to understand how these things work. Okay, so let's start up Godot and do a simple shader. So let's see. So here's Godot. I'm going to just start a new project. Close all scenes. I don't know. Let's start it up again. Okay, you're going to create a new project. You're going to put it in a location. It's not going to be super heavyweight like a Unreal project, so you don't have to worry about it like blowing up your home directory. And it also doesn't have to like copy 1,000 things in and then compile shaders for 10 minutes. So these are all good things. If you've used Unreal, you know what I'm talking about. We're just going to put this in advanced shading. And we're going to give it a name. Okay. Okay, so it's starting up. This is how long it takes to start a new project. This is why we're not using the others. Now, you're going to want to stick a file, like your geometry, in the folder that you just made. So I'm going to take this object here, and I'm going to put it in this folder here. That makes it easy to find the resource. Now when you start a Godot scene, you're going to need to specify a root node. We're going to create a 3D scene, and then we're going to create a new entity, and it's just going to be an instance geometry. Mesh instance. Once you have a mesh instance object, you can then choose the mesh. It will show here in this list anything you've put in that directory. You can put whatever geometry in here that you want to. And by default, this is what's going to happen. It's going to bring you your geometry and light it and render it. Everything's going to be happy. However, we want to do our own shader. So once we have our mesh instance 3D, we can click to surface material overrides. And where it says empty, we're just going to click this button, or we're going to click this drop down button, and we're going to say shader material. And then we click on the shader material. We click on the shader ball, it'll bring up this thing, and it says what shader you're going to use. Right now it's set to empty. We're going to say a new shader. And this is going to make a new GD shader text file. If you create it, there's different modes for the way the shaders can behave. Spatial is the one we want to use. It's the default. And it has a default template, which is nice, so you don't have to type everything in. And we're just going to say create. And now we've got a text file over here. If you double click on this text file, it'll open up the text editor. Godot has a reasonably good text editor with autocomplete and pop-ups and stuff like that. And so now we have this shader attached to this object. And if we want to set this color, we put albedo, and we say this is equal to a color. So remember how I said it's really picky? So the data types that you're interested in, a color is called a vec3f, which means a vector 3, which means it has 3 floats, or has 3 entries and their floats. So we do a vec3f, and then we can do in parentheses the values we want. So if we want to do this red, we'll just do 100, and oh, sorry, vec3. This is the problem of using multiple shading languages. Because the last shading language I was using for hardware stuff, you had to say vec3f. So thanks, Alec. So now we've made our object red, right? Okay. What else can you do? The lighting is also happening. If you want to override the way the lighting happens, you can just uncomment this light section, and then this is where I got to check the documentation because I don't remember it all. Oh, if you click online docs, it'll pop up the documentation, and we can click on the spatial shader documentation, and it will give us. I'm not going to explain render modes. It's like if I was to get into all the intricacies of hardware shaders, this would be, I don't know, at least half a semester or a whole semester. We're not going to do that right now. Just suffice to say, there's a lot of complication to the way that hardware shaders work. So this will tell us what built-in variables you have that you can use. So all these things in all caps are built-in variables. Like we can get the camera direction in world space, the camera position in world space. We can get the, let's see, eye offset is good for, okay. So vertex is the current position. It is not in world space, it's in current space, which means it's in the space where it's been transformed into the view of the camera. And there's tangent binormals, and you can access your UVs and things like that. The lighting function. So if you want to do light, this is what normally is happening, plus the specular component. So if we add this in, now our object is lit, right? So now it's not as bright. If we want to make this gray, okay, now it's a gray thing and it has diffuse lighting, right? If you don't want lighting, you can just override this. And we could just say albedo, because that's a built-in, and now it's just a constant shader.
Why would, in which cases would we want to change the lighting or like play with lighting?
Let's say you want to do cell shading, or you want to do wrap lighting, where the lighting extends a little bit beyond the terminator, or you want to implement a velvet shader or something like that. You might change this block of code here. Okay, so that's the basics of how you start this up. Texture maps are, okay, let me give you a couple more things and then we'll move on to some more theory. If you want to expose a parameter, it's called a uniform. So if you type uniform, float, we're going to do frequency equals 1, and then we're going to make a pattern here. And we're just going to do sine of, we're going to use the vertex position dot x, and we're going to multiply it by frequency. And we're going to cast that to a vec3. Okay. Now if this compiles, now you see that this is locked into screen space, right, or into camera space. So when we move our object, this pattern doesn't move with it. That's fine for our example. Now if we click back here to mesh instancer, and we find our shader, there's now shader parameters, and anything that you put in here as a uniform becomes exposed to the UI. So now you can change the parameters. So this is how you would change things. Texture maps. The way textures work in hardware is that you're actually binding a texture map to a texture sampler. So if we say so now we have a, let's see, is this the right way to do it for this? No, it says expect a constant. Okay, so now we say uniform texture 2D my texture. and equals sampler 2D. Hopefully I've got the syntax right on this. Or no, sorry, sampler 2D. There, my texture. Constant to sampler 2D. Okay, are we happy? Okay, so now we got a sampler 2D. Once we have a sampler 2D, now we have a texture reader. So I'm going to stick a texture in this folder. Oh, I'm going to use the power box textures. Okay, so here's our base paint. And I guess I have UDIMs on this thing, so may or may not work, but let's pop this texture into the folder. And now if I grab that texture, okay. And if I assign the albedo to let's cross our fingers I've got this right. Okay, so this is going to return a vec4 by default. So we're just going to say XYZ. And now we've loaded a texture. Okay, so let me explain a couple of things. This is how you can reference pieces of a vector. This is the swizzle. This whole thing is how you swizzle things. I know that sounds silly, but if I wanted to do XXX, I could type that and it will give me just the red channel shuffled into the red, green, and blue channels. I could also do a YXZ if I wanted to reverse it. YZX, and it should read these in backwards. So changing the ordering of the letters here allows you to address specific channels from your texture map and return the result as the desired data type. So if I was trying to assign this to a float, I would just do an X. And I'm doing XYZ, so that'll read the XYZ textures. The alpha channel we're going to ignore. The texture command is always going to read 4 channels, and it's always going to return 4 unless you otherwise specify. Okay. You can multiply these results, like if I wanted to multiply that by the pattern I was making, I could do that. Okay. So now I'm scaling the texture map by that. So you can do all the same types of things you might do in the OSL shader. You can do them here. And that leads me to the end of my brief lecture on how to use this. And now we're going to talk about some theory about how shaders work. Any questions? Okay, I'm going to stop the recording.